Hello everyone. Let us continue the third part of today's class. Okay, so the strategy profile of all users and the strategy profile of all users except user N are denoted by sigma is equal to sigma I is equal to 1 to N, and sigma minus I is equal to sigma I is not equal to N respectively. The reward for user N at time t, Rn of t depends on its action. Okay, An of t minus 1, and the actions taken by all other users at time t minus 1. So the small n denotes the reward. Okay, do you remember what does capital R denotes? Okay, the capital R denotes the regret. Okay, let us review it. Okay, capital R here is the regret. Okay, that is the unknown network state that user N aims to learn. In practice, the reward represents a function of the data rate, latency, etc. We define the accumulated discounted reward by capital R of N, capital Rn is equal to summation small t is equal to 1 to capital T, gamma to the power of t small t minus 1 times small rn of t, where 0 is smaller than or equal to gamma, and gamma is smaller than or equal to 1 is a discounted factor, and capital T is the time horizon. What is time horizon? Let us see the handout. Okay, page 63. Problem 1. What is time horizon? Solution. A time horizon, also known as a planning horizon, is a fixed point of time in the future at which point certain processes will be evaluated or assumed to end. Okay. Let the expectation of capital Rn of sigma n and sigma minus n denote the expected accumulated discounted reward when user n performs strategy sigma n and the rest of the users perform strategy profile sigma minus n. Then the objective of each user, say n, is to find strategy sigma n that maximizes its expected accumulated discounted reward. The maximum of the expectation of capital N Rn of sigma n and sigma minus n, where sigma n is the variable. Okay, next let us go to section 1.3.2, distributed learning, game theoretic and matching approaches. In this subsection, we discuss related works that use game-theoretic models, distributed optimization and learning and matching techniques, and that were proposed in past and recent years for related models. Very recent developments based on deep learning will be discussed later. Okay, Aloha-based protocols and cross-layer optimization. What is the cross-layer optimization? Let us see the handout. Okay, sorry, not this. Okay. Okay, page 65, problem 1. What is cross-layer optimization? Solution. Cross-layer optimization is an escape from the pure waterfall-like concept of the OSI communications model with virtually strict boundaries between layers. Okay. Let us go back to the slides. So, Aloha-based protocols have been widely used for spectrum access, primarily because of their easy implementation and random nature. Related work on Aloha-based protocols can be found in, first, Pontorakis and Saikas in 1992. Let us see this reference. This Pontorakis and Saikas analysis, stability and optimization of Aloha-type protocols for multi-channel networks, computer communications, published in 1992. Second, McKenzie and Wicker in 2001. Here, McKenzie and Wicker, Selfish Users in Aloha, a game-theoretic approach, IEEE Vehicular Technology Conference in 2001. And the third reference is Jean and Cassidy's in 2002. Let us see Jean and Cassidy's Equilibria of a non-cooperative game for heterogeneous users of an Aloha network, published in IEEE Communications Letters in 2002. Next, Shen and Lee in 2002. Shen and Lee, Stabilized Multi-Channel Aloha for Wireless OFDM Networks, published in the IEEE Global Telecommunications Conference, GlobalCom, in 2002. Next is the Altman et al. In 2004. We can see that here. Altman et al. Slotted Aloha as a game with partial information, which is published in Computer Networks in 2004. Next is Bai and Zhang in 2006. Bai and Zhang, Opportunistic Multi-Channel Aloha, Distributed Multi-Access Control Scheme for OFDMA Wireless Networks, which is published in IEEE Transactions on Vehicular Technology in 2006. Next is the Manachi and Shimkin in 2008. Manachi and Shimkin, Rate-based equilibria in collision channels with fading, which is published in IEEE Journal on Selected Areas in Communications in 2008. Okay, next is Toh and Choi in 2010. Okay, let us see. Toh and Choi on exploiting idle channels in opportunistic multi-channel Aloha, which is published in IEEE Communications Letters in 2010. Okay, next is the Cohen et al. In 2012. Okay, Cohen et al. In 2012. A game theoretic optimization of the multi-channel Aloha protocol in International Conference on Game Theory for Networks, GameNets, in 2012. Okay, next page. Cohen et al. In 2013. Okay, we can see that Cohen et al. Game theoretic aspects of the multi-channel Aloha protocol in cognitive radio networks, which was published in IEEE Journal on Selected Areas in Communications in 2013. Okay, next is the Cohen and Leshem in 2013. Okay, Cohen and Leshem distributed throughput maximization for multi-channel Aloha networks in IEEE 5th International Workshop on Computational Advances in Multi-Sensor Adaptive Processing, CAM-SAP, in 2013. Next is the Cohen and Leshem in 2016. Okay, Cohen and Leshem distributed game theoretic optimization and management of multi-channel Aloha networks, which is published in IEEE ACM Transactions on Networking in 2016. Okay, the last one is the Wu et al. In 2013. Okay, we can see that Wu et al. FASA accelerated S-Aloha using access history for event-driven M2M communications, which is published in IEEE ACM Transactions on Networking in 2013. For fully connected networks where all users interfere with each other, and in first, Carr et al. 2004. Okay, Carr et al. Achieving proportional fairness using local information in Aloha networks, IEEE Transactions on Automatic Control in 2004. Okay, second is Wang and Carr in 2006. Okay, we can see that Wang and Carr and cross-layer rate optimization for proportional fairness in multi-hub wireless networks with random access, IEEE Journal on Selected Areas in Communications in 2006. And the third one is Bassley et al. In 2006. Okay, we can see Bassley et al. An Aloha protocol for multi-hub mobile wireless networks, IEEE Transactions on Information Theory in 2006. Okay, the fourth one is the Kaufman et al. In 2007. Okay, we can see that Kaufman et al. Measurement-based self-organization of interfering 802.11 wireless access networks in proceedings of IEEE International Conference on Computer Communications Infocom in 2007. Okay, next is the Basile et al. In 2009. Okay, we can see that Basile et al. In 2009. Stochastic analysis of special and opportunistic aloha. IEEE Journal on Selected Areas in Communications in 2009. Okay, the next one is the Gupta and Stoyer. Okay, in 2012. Okay, Gupta and Stoyer. Throughput region of random access networks of general topology, which is published in IEEE Transactions on Information Theory in 2012. Okay, next is Chen and Huang in 2013. Okay, Chen and Huang, distributed spectrum access with spatial reuse, which is published in IEEE Journal on Selected Areas in Communications in 2013. Okay, the next is Ho and Gupta in 2014. Okay, we can see that here. Ho and Gupta, proportionally fair distributed resource allocation in multi-band wireless systems, which is published in IEEE ACM Transactions on Networking in 2014. And the next one is the Cohen et al. In 2015. Okay, Cohen et al. In 2015. Okay, distributed learning algorithms for spectrum sharing in spatial random access networks in International Symposium on Modeling and Optimization in Mobile, Ad hoc and Wireless Networks, YOPT, in 2015. Okay, you can click on this DOI and your browser will direct it to the page of this paper. Okay, like this. Okay, let us go back to the slides. Okay, and the final one is Cohen et al. In 2017. Okay, we can see that Cohen et al. Distributed learning algorithms for spectrum sharing in spatial random access wireless networks, which is published in IEEE Transactions on Automatic Control in 2017. Okay, these are for spatially connected networks where each user interferes with its neighbors only. Then opportunistic Aloha schemes that use cross-layer techniques in which the design of the medium access control MAC layer is integrated with physical layer 5 channel information to improve spectral efficiency, have been studied under both the single channel, which includes the following 3 publications. First is Bai and Zhang in 2006. We can see that Bai and Zhang, opportunistic multi-channel Aloha, distributed multi-access control scheme for all FDMA wireless networks, which is published in IEEE Transactions on Vehicular Technology in 2006. And the second one is Manetchi and Shinkin in 2008. Manetchi and Shinkin, rate-based equilibria in collision channels with fading, which is published in IEEE Journal on Selected Areas in Communications in 2008. The final one is the Besley et al. In 2009. Besley et al. In 2009. Stochastic analysis of special and opportunistic Aloha, which is published in IEEE Journal on Selected Areas in Communications in 2009. And multi-channel. Note that these 3 papers are for single channel, and the following 1, 2, 3, 4, 5, 6 is for the multi-channel case. The first is Bai and Zhang in 2006. Bai and Zhang, opportunistic multi-channel Aloha, distributed multi-access control scheme for all FDMA wireless networks, which is published in IEEE Transactions on Vehicular Technology in 2006. The second one is Tu and Choi in 2010. We can see that Tu and Choi on exploiting idle channels in opportunistic multi-channel Aloha, which is published in IEEE Communications Letters in 2010. The second one is Cohen et al. In 2012. We can see that Cohen et al. A game-theoretic optimization of the multi-channel Aloha protocol in International Conference on Game Theory for Networks, GameNets, in 2012. The fourth one is the Cohen et al. In 2013. Cohen et al. Game theoretic aspects of the multi-channel Aloha protocol in cognitive radio networks, IEEE Journal on Selected Areas in Communications in 2013. And finally is Cohen and Leshen in 2016. Cohen and Leshen distributed game theoretic optimization and management of multi-channel Aloha networks, IEEE ACM Transactions on Networking in 2016. Cases. Other recent related studies considered opportunistic carrier sensing in a cross-layer design to exploit the channel diversity to optimize a certain objective. Okay, it is 25 minutes. Let us take a break.